In module 6.1, we introduced this idea of modeling degradation of materials with time. And we talked about increasing parameter value or decreasing parameter value and how that could be captured through a simple power law form. And we defined a degradation rate, which is very critical. And that degradation rate we saw was always positive, and depending on the index m value being less than 1 or equal to 1 or greater than 1, you could capture the three phases of the bathtub curve with decreasing failure rate, constant failure rate, and increasing failure rate. So in module 6.2, we'll work out a simple example to illustrate the power law degradation rate model. So in this example, a metal component corrodes with time. The oxide layer growth with time is shown in the table here. Initially, the oxide layer thickness was 1 micron. At the end of year 1 was 2.1 microns, year 2, 2.4 microns, and year 3, 2.6 microns. And we are then asked to find the power law equation that best fits the data. This is typical of reliability modeling. We will have experimental observation, and we would want to fit a model to this sort of an experimental observation. Extract parameters to describe this degradation process. So first question is, find the power law equation that best fits the data. What is the expected value of oxide thickness after 10 years? So we have data for 3 years. We want to predict out to 10 years. And this is also typical in reliability modeling. So we would use a mathematical model to predict what would happen in future. What is the anticipated failure population at a given time? If I have, so let's say I have field failures in a given product, and I might have the early phase, I might have like 2 or 3 failures, and then I would want to be able to predict what would happen, when would I have my 10th failure, etc. So I want to be able to model, and usually you adaptively model. Then the next question is the degradation rate increasing or decreasing with time? And what is the time it takes for the oxide thicknesses to become 3 times the original thickness? The original thickness was 1. The question here is, what is the time it takes for the thickness to become 3 microns, 3 times the original thickness? Now, as with any data fitting type problem, it's very convenient if you could use the mathematical tools that we have at our disposal, the programs that we have at our disposal. In our case, it is Octave, and that's what we are going to use to do this modeling. So let me start with defining the problem. So first I'm going to define time. Time to failure. Time to failure goes from, I'm going to define time to failure going from 1 to 3. Okay, times of observation. I shouldn't say time to failure. I should say times of observation going from 1 to 3. Okay. My initial parameter value, S naught, I'm going to define to be equal to 1. That was the initial thickness, 1 micron. And the observed thicknesses at times 1, 2, and 3 years is 2.1, 2.4, and 2.6. Okay, those are my observed thicknesses at times 1, 2, and 3. So now I'm going to use the linearized form. So I'm going to define x to be log of t. So the function is log of t. Okay, and it'll give me those 3 values. Log of 1 is 0, log 2 is 0.69315, and so on. Now I'm going to define my y-axis, And this is, as I notice here that this is a problem with increasing parameter values. So the form that I need to use is the one that corresponds to increasing parameter values. So what I'm going to do is for y, I'm going to choose the value to be log of, remember, log of s minus s naught divided by s naught. That's what I'm going to choose to be the y-axis. So I've got my y values now. So now I need to do a fit between x and y. Okay, and in Octave, as in MATLAB, the fit command, I'm going to call those pfit as a variable. I will explain this pfit in a minute. So the function that allows you to do a polynomial fit is the function called polyfit. In polyfit, you fit x versus y, and you describe the polynomial degree that you want to fit between x and y. Here, the degree is a straight line. Therefore, if we want to fit a straight line between x and y, because x and y are in log form. And remember, this is the linearized form. Therefore, I want to choose a parameter value of 1 for polyfit. And this, in turn, when I fit a straight line, I'm going to get two quantities as a result of that fit. Those two quantities will be assigned to pfit. The quantities are slope and the intercept. So I'll have two values, the slope and the intercept. So the slope value I'm going to assign to the variable m. M is pfit of the first element of the pfit is what I'm going to assign to slope. And similarly, c intercept is negative of pfit of 2, and the negative because of the form that we had in our expression there. Okay. So now my time scaling constant is related to this c intercept c. So this is going to be x, it's going to be obtained as exponential of c divided by m, simply because the intercept was m log ts, negative of m log ts. So ts is obtained as exponential of c over m. Okay, and that's 0.75. And that's my ts. And that gives me a time constant. Okay, rough order of time, that's 0.75 years is my time constant. So now I can go ahead and ask the question or answer the question, what is my expected thickness at 10 years? I'm going to call that S10, and S10 is S naught times 1 plus 10 divided by Ts raised to the power m. Okay. This whole thing. So S naught times 1 plus T over Ts to the power m. So that's what we have here, corresponding to time of 10 years. So I do that and I get my value to be, my thickness value that I can expect at the end of 10 years to be 3.419. And you can also calculate the time it takes for you to reach 3 times the initial thickness. So I'm going to define a new S sub f, which is basically the thickness at failure, and that's 3 times S naught, which is 3 microns. So now I can go ahead and calculate the time to failure. Time to failure is going to be Ts times SF minus SF divided by S naught minus 1 raised to the power 1 over m, raised to the power 1 over m. Okay, so that's going to give me the time it'll take for the thickness to reach the oxide thickness to reach 3 microns. That's 5.7 years. And the last question was, what is the rate increasing or decreasing? It appears from what we are seeing here that the rate is decreasing because it takes 5 years to go from or 4.3 years to go from 3 microns to 3.4 microns. So I'm going to guess this is a decreasing rate. But let's calculate the rate and see if that's indeed the case. So the rate is m divided by Ts times T over Ts. Now you have to remember that in Octave, as in MATLAB, all your parameters are matrices. Like for instance, this T is actually a row vector now. It has 3 values corresponding to 2.1, 2.4, and 2.6. However, an important, powerful feature of MATLAB and by extension Octave is that you can carry out this operation on a matrix of values. And in order to do that, you, instead of raising it to the power m minus 1, if you put a dot before that power operation, that dot would apply whatever follows, the operator that follows to each element of my array T. So what I'm going to do is dot m minus 1. Now this is equivalent to taking the first element of T to first element of T, which is 1 raised to the power m minus 1, second element of T raised to the power m minus 1, third element of T raised to the power m minus 1, and giving me a result which is an array as well. So this rate will have 3 values corresponding to the 3 different times. And now if you notice, this m value here is less than 1. So there right away we know that the value of m less than 1 corresponds to decreasing failure rate. So, and indeed what you'll find is the rate is actually decreasing. So the oxidation rate is indeed decreasing with time. So that I could have told right away by looking at the m value. Okay, so that's an example of how you do data fitting using these degradation models. We used a very simple degradation model, a power law model. And the process we use to fit this power law model is exactly the process we will use later to fit to other degradation models, such as a log normal or Weibull degradation models. The process will be very similar. And in fact, many of the concepts, such as this m having a value less than 1 for decreasing failure rate, equal to 1 for constant failure rate, increasing failure, greater than 1 for increasing failure rate, you'll find that it will come back again when we discuss Weibull distribution. Okay, I will end module 6.2 with this.